this is in continuation my earlier tutorial classes. This is tutorial 4. This basically based on my lectures in the 4th, 5th and 6th week, that is from 16th lecture to 20th lecture, we will take up first. So, the exercise which we discuss is following. So, that the sequence Bn where Vn is 1 over n plus 1 whole square, 1 over n plus 2 square, and n plus 1 by 2n whole square converges to 0. So, this is the question. So, that this sequence, this is the one term of the sequence, and a term you can say A, when n tends to infinity, the sequence converges. Now, in order to show it is converging to 0, we will use the sandwich theorem. What is the sandwich theorem? The sandwich theorem says if An's are less than or equal to Bn, less than or equal to Cn for every n, and the limit of An as n tends to infinity is the same as limit of Cn as n tends to infinity, and both are say L, then the limit of Vn as n tends to infinity will also be L. So, using this sandwich theorem, we will prove that limit of Bn will go to 0. So, in fact, we have to first establish this identity where the Bn lies between A and Vn for all n. Now, clearly the Vn lies between 1 by n square into n and 1 by 2n square into n, because the term this n plus 1 square is greater than or equal to n square. So, 1 by n plus 1 square is less than n square. So, each of this term is less than 1 by n square, and total number of terms is n. So, the Vn will be less than or equal to n times 1 by n square. Similarly, this term is the least one. So, Vn will be greater than or equal to 1 by 2n square into n. Now, this is the same as 1 by 4 n, which is less than or equal to Vn, less than or equal to 1 by n. Now, this is our An's, this is our An's, this is our Cn's. So, limit of An and Cn's here as n tends to infinity is nothing but 0. Therefore, limit of Vn as n tends to infinity will also be 0. So, it is very easy to establish this one. Okay? So, this is the second example is so that the sequence An's defined by the formula A n plus 1 equal to square root of 3 times A n, where the first term A 1 is given to be 1. So, that this sequence converges to 3. Solution. Now, here we will use first by mathematical induction, we will show that this sequence n is a monotonically increasing sequence, and then we will also show it is a bounded sequence. So, we know a bounded monotonic sequence is bounded monotone increasing sequence is convergent. If a sequence is bounded and its monotonic increasing sequence, then it must be a convergent sequence. Similarly, if a sequence is decreasing, monotonically decreasing and bounded below, then it is also convergent. So, basically in order to show the limit of this is 3, we will show that this sequence is first a monotonic increasing sequence, it is also a bounded sequence, and the upper bound is nothing but 3. So, when you go the limit for this, we will establish the limit exists and will come out to be the 3. So, let us see how to find. What is our a 1? A 1 is 1, a 2 comes out to be root 3, a 3 comes out to be square root of 3 into root 3, and continue this. This is our different term. So, obviously, a 2 is greater than a 1. It is further similarly, a 3 is greater than a 2, greater than a 1, and continue. So, we can assume that a m plus 1 is greater than a m, where m is 1 to 3. Now, this implies that root 3 times a m plus 1 is also greater than root 3 times a multiply by root 3 and then take the square root. So, both entire. So, we get this, but this is nothing but what a m plus 2 by definition is greater than a m plus 1. So, this is holds true. Therefore, a n is a increasing monotonic increasing sequence. Okay. Now, second we establish that this is basically a bounded sequence. Now, a 1, since a 1 is giving to be 1 which is less than 3, then what is a 2? A 2 is 3 into a 1 under root. So, this is also less than 3 because a 1 is less than 3. So, square of 3 into a number which is less than 3 cannot be 3, therefore, it is less than 3. Similarly, we can say that a n is less than 3. Okay. Now, same case multiply by 3. So, 3 a n is less than 3 into 3 square root. So, this is 3. So, this shows a n plus 1 is also less than 3. Therefore, the sequence a n is a bounded sequence, bounded above by 3. Okay. Therefore, it will have a limit. So, by above theorem, so the limit of a n as n tends to infinity is say L will exist. By the result that every bounded monotonic sequence bounded above is convergent, has a limit L. So, now start with this. So, consider a n plus 1 which is giving to be 3 a n square root, take the limit as n tends to infinity. Taking limit as n tends to infinity, a n plus 1 is equal to under root 3 into limit of a n as n tends to infinity within the square root. So, this implies that L equal to root 3 L, and when we square length this, so solve it, we get either L is 0 or L is 3. clear. Square L square is equal to 3 here. So, L into L minus 3 is there. So, L equal to either 0 or 3, but L cannot be 0. L is not 0. Why? Because the first term a 1 is 1. So, limit cannot be less than 1. Therefore, L is equal to 3, and that is the answer for it. Okay. So, this is what I hope it is correct. Means because it is each term is a 1 is 1 and the terms are of increasing nature. So, that is why we are not getting a limit less than 1. It is always be more than 1, therefore, it will be 3. So, it is 2. The third example is, if Sn, if a sequence Sn is a sequence such that Sn plus 1 is equal to under square root AB square plus Sn square divided by A plus 1, where the V is greater than A, strictly greater than A for every n greater than equal to 1. Okay. And let S1 is A which is greater than 0. Then so that the sequence Sn is an increasing sequence and bounded above. So, solution is. So, same trick we will apply using the induction. We will show first S2 is greater than S1, then we will show S3, Sn is greater than Sn minus 1, and then finally, by induction Sn plus 1 is greater than Sn will show that it is always be increasing sequence and then bounded in a similar way. So, let us consider for n is equal to 1, the S2 from the given formula comes out to be AB plus S1 square divided by A plus 1. Now, this is equal to square root AB, S1 is given to be A. So, AB square, this is AB square. So, AB square plus A square divided by A plus 1, this is S2. So, what will be the our S2 square minus S1 square? If we simplify this thing, this square minus A square and solve it, we get the result A B square minus A square divided by A plus 1. Now, since B is greater than A, so this part is positive, A is already given to be positive, therefore, this is greater than 0 as B is greater than A is greater than 0. So, this shows that S2 is greater than S1, first thing. Now, assume this result true, Sn is greater than Sn minus 1 is true for n is greater than equal to 1. Then consider Sn plus 1 whole square minus Sn square, and now this will be Sn square. This will be equal to AB square plus Sn square divided by A plus 1 minus Sn square minus Sn square, of course 1. So, this is equal to, when you simplify further, you are getting A into b square minus s n square divided by a plus 1. Now, since a is less than b, s 1 which is a less than b, and b square minus s 2 square is nothing but the v square minus a square by a plus 1, which is also positive. So, from here we get see that this will be conduction. So, this will show that S 2 square is less than B square, and similarly by induction we can prove that Sn B square is less than B square. This is we are assuming, is it not? Here we will show that is true, that is from here we are assuming. Since this is true for n, so we are taking this is assuming, therefore, this part Sn Sm square minus Sn square will be negative. So, Sn square, sorry, this is S 2 is greater than 0. So, B S 2 square S B square minus S 2 square, this is wrong, is it? Is not. B square minus S 2 square is B square minus A square by A. So, this shows that S 2 square B square minus S 2 square is less than B square. Okay. So, B square minus Sn square is negative, therefore, this part will be negative. So, this shows that our sequence Sn is Sn by method of induction, this Sn lies between 0 and B. So, it is a bounded sequence for this. So, this sequence is bounded. So, sequence is bounded. Okay. So, what we did it, we have first started with n equal to 1. We have shown that S 2 is greater than S 1, and similarly by induction we can prove Sn square minus Sn square. This is coming to be the V square minus Sn square by A plus 1, which is nothing but same as A into V square minus 1, but since A 1 S 1 is less than this, and this is Sn square is less than Bn square, this we can we are assuming for that. So, this is positive, therefore, it is a increasing sequence, and then further we are taking Sn plus 1 by this. Okay. So, we get from here a Sm is plus 1. In fact, we can show one more term is Sm plus 1 whole square minus B square. This we can prove as AB square plus Sm square divided by A plus 1 minus B square, and that comes out to be Sm square minus B square over A plus 1, which is negative because this Sn square is less than B. So, this will be always bounded sequence, therefore, this is because of this part. Okay. So, this proves it is a bounded sequence and increasing sequence. So, this the next result so that the limit as n tends to infinity m minus 1, m minus 2, m minus n plus 1 divided by factorial n x to the power n is 0, where the mod x is less than 1. m is fixed, m is fixed. So that now here we will prove the result by using the test. We know the ratio test in case of sequences. What the ratio test says? If limit of a n plus 1 by a n as n tends to infinity is suppose L, and where L lies between minus L2 plus 1, L lies between minus 1 to plus 1, then the limit of a n will be 0. Will be 0. Means if n is a sequence of real number, whether they are positive or negative, and if the limit of this ratio is coming out to be number L, which lies between minus 1 to plus 1, then limit of the sequence a n must be 0. So, using this thing. So, let us see here what is our a n here. Here, if I choose a n to be m, m minus 1, m minus 2, m minus n plus 1 divide by factorial n. So, a n plus 1 divide by n, this is equal to n plus 1. So, n equal to n plus 1. So, last term will be m minus n, and here factorial n plus 1. So, if I divide, we are getting m minus n over n plus 1, this thing, limit of the into x, and then take the limit as n tends to infinity. So, this limit will be equal to m by n minus 1 over 1 plus 1 by n as n tends to infinity x, and that comes out to be minus x. Now, it is given that mod x lies between 1. So, this limit x is lying between minus 1 to plus 1. Therefore, the limit of this a n plus 1 by a n as n tends to infinity lies between 1 and minus 1. Hence, the limit of a n as n tends to infinity must be 0 according to this result, ratio test. By ratio test. Okay. So, this one. Now, in the ratio test, there is another also. If the limit of this, say L, which is greater than 1 and each term is positive, then it will be infinity. So, another example shows the ratio test when the limit comes out more than 1. So that the sequence a n, which is factorial 3n divided by factorial n cube power 3 is divergent. Okay. Solution. Again, we use this ratio test. What is the ratio test is? If n's are positive, and limit of a n plus 1 y n when n tends to infinity, the absolute value of this is say L, where L is greater than 1, then limit of this a n's as n tends to infinity is infinity. In fact, it will be plus infinity. Okay. So, using this result, we will prove it. So, consider here a n plus 1 divided by a n. So, what is the a n plus 1 by a n? That is equal to factorial 3n plus 3 divided by factorial n plus 1 into factorial n cube sorry, this is cube, and then 3n factorial. So, if we simplify this part, we are getting the limit of this as n tends to infinity is nothing but limit of 3n plus 3, 3n plus 2, 3n plus 1 divided by n plus 1 whole cube. So, take n outside and we get limit as n tends to infinity 3 plus 3n, 3 plus 2n, 3 plus 1 by n divided by 1 plus 1 by n cube, and that comes out to be 27 greater than 1. Therefore, limit of a n as n tends to infinity is infinity. So, this is also interesting results for this. Now, one more Cauchy results we will show. So that limit 1 plus root 2 plus cube root of 3 plus nth root of n divided by n is 1 as n tends to infinity. So, solution is again it based on the Cauchy theorem. What is the Cauchy theorem says? The Cauchy theorem says if the sequence ans converges to L, then the sequence xn, which is equal to a1 plus a2 plus an by n, will also converge to L. So, here ans are n to the power 1 by n, and limit of this as n tends to infinity n is 1. This is the limit, because suppose y is n to the power 1 by n, take log y. So, it is log n by n, take the limit as n tends to infinity, then this infinity by infinity form, apply the L'Hospital's rule. So, we get limit of this as n tends to infinity is 0, therefore, y is 1. So, limit of this is 1, hence the limit of each term a 1 is 1 plus root 2 plus cube root by 3 plus nth root by n divided by n, limit as n tends to infinity is also 1, and that completes the proof. Okay, thank you.